Okay, so today we're gonna start off with acid-base equilibrium. And so what we need to first do is identify who our strong acids and strong bases are. So our first strong acid is hydrochloric acid, HCl. HBr, HI, HNO3, H2SO4, and HClO4. So all 6 of these are our strong acids. So if you are an acid and you are not one of these, you are considered a weak acid. Okay. So the 8 strong bases are every single alkali metal with hydroxide. So if you go down your first family on your periodic table, you have lithium, right? That's the first alkali metal, hydroxide. Oop, oop, oop. Okay. We don't do FROH because it's radioactive and we're just not going to pay attention to it. So you've got all of these alkali metals with hydroxide. They're all strong. And then 3 other ones from your alkaline earth metal family. That's your second family. CBS, calcium, barium, strontium. Okay, now remember that your alkaline earth metal family is +2 and hydroxides are -1. That's why you see the OH in parentheses with 2, because calcium is +2, hydroxide is -1, so you need 2 hydroxides to balance it out. Now you don't see that with your alkali metals because they are +1 and hydroxide is -1, +1, -1. So those go together perfectly. Okay, so these are your 8 strong bases. If you are not one of these 8 strong bases, by default, you are a weak base if you're a base, okay? So if you're not strong acid, you're a weak acid, and if you're not a strong base, you're a weak base. Obviously, there are tons and tons and tons and tons and tons and tons of acids and bases. So as long as you know who is strong, which are not very many of them, by default, everybody else is weak. So it's just easier to just know who all of the strong ones are. So if I say, hey, acetic acid is this. Okay, acetic acid. It's an acid. Is it a strong acid? No. Why? Because it's not one of my 6 strong acids. So what kind of acid is it? It's a weak acid. This right here are just examples of strong acids and weak acids, as well as strong bases and weak bases. Again, we went over the strong ones, and then these are just examples of some weak bases that you might see here and there. Notice HF is a weak acid, which can get kind of confusing, right? Because you see hydrogen with this halogen, and this halogen, and this halogen, yet HF, which F is a halogen, is not strong, okay? So what are some properties of acids and bases? Acids have like a sour taste. You notice this a lot in like fruits, like lemons, oranges. Acetic acid is a main component of vinegar. And acids just have like that sour property. Okay, whereas bases are the opposite. They have like the bitter taste. So like broccoli is pretty basic. Most bases, or bases in like liquid form, obviously feel slippery. So things like soap is also basic. So think about soap being slippery. And also like drain cleaners and things like that, they have potassium hydroxide, which is one of our strong bases in it. And so that's another example of basic, okay, something that's basic. We are going to talk about the first and second acid-base ways to talk about acids and bases. And then the third way we will not discuss, but I just wanted to present to you that there are more than 2 ways to identify an acid or a base. This first way is kind of what we've been doing so far this year. So an Arrhenius acid, Arrhenius is just the scientist's name, is basically something that has H plus in it. It produces hydrogen ions. So this definition says if you give off hydrogen ions in a solution, you're an acid. And the Arrhenius base definition says if you produce hydroxide ions in solution, you're a base. It's a very generic statement, but it has kind of worked so far. So look at like NaOH, has OH in it, it's a base. KOH, has OH in it, it's a base. Calcium hydroxide, has OH in it, it's a base. Okay, this works so far. And then this was the main way we recognized an acid. I told you when we were learning how to name acids that if there is a hydrogen out front, it's an acid. So again, they're saying H something. What does this A mean? It could be whoever. HA, HCl, HBr, HF, HNO3, H whatever. They're saying it could be whoever that thing is. So HCl, HNO3, H whatever. And again, the presence of the H out in front when ripped apart and producing hydrogen gives us an acid, okay? And this works a lot of the time. This type of definition works a lot of the time. But unfortunately, it doesn't work all of the time because and it's usually because of the bases, not all bases that we know have hydroxide in them, and yet they're still basic. So while this does work, it isn't foolproof. Like there are other bases that don't produce hydroxides. For example, does anybody remember that guy's name, NH3? It's ammonia. And it is a common household item used for cleaning. It is a base. Do you see OH minus in there? I sure don't, yet it's a base. So this definition of acid and a base would not have included this guy as a base, yet it is a base. So this is a decent definition, but it doesn't cover all of the acids and bases that do exist in our everyday life, okay? So again, these the problems with the Arrhenius acid base is this base only works if you have hydroxide ions in it. And look, I gave you 2 examples. Baking soda is also basic. Its name is sodium bicarbonate. It's a weak base, but it doesn't have OH in it, yet it's a base. So this Arrhenius acid and bases works for a lot of things, but it doesn't work for everything. Okay, its definition doesn't cover all acids and bases. So what we're going to work on today is 2 things. We're going to work on a new way to identify an acid or a base. It's called the Bronsted-Lowry model. And then we're also going to start working on calculating pH. So if you don't have your calculator handy, you're going to want to go find it. You're going to need it, please. But a Bronsted-Lowry acid is something that gives away a hydrogen ion. Now, what is a hydrogen ion? It is an H+, okay? Hydrogen ion. A Bronsted-Lowry base accepts or takes in the hydrogen ion. And this forms what are called conjugate acid-base pairs. Once I start doing some practice, this will make more sense, okay? So this definition of acids and bases helps us encompass more acids and bases than the Arrhenius definition did, all right? So we're just going to focus on where the hydrogen is moving to within the reaction. So let me give you an example. This is a generic example. Again, notice HA. Let's just pretend. I'll call it HF, where the A is F, right? A isn't a real thing. They're saying just a generic, okay? And then this is some base, B. Well, if you notice over here, the base has accepted the hydrogen ion. Now, since the base was neutral and the hydrogen is +1, it becomes BH plus 1. Whereas the acid has lost the hydrogen ion. Look, this had a hydrogen ion on it, and now it doesn't. Well, if you lose a plus 1 charge, you become minus 1, okay? So now what are the pairs? Well, the acid lost the hydrogen ion, so this is called its conjugate base. Whereas the base, from here to here, accepted the hydrogen ion, so this is called its conjugate acid. An acid will always be with a base, and a base will always be with an acid. Conjugate acid-base pairs hook up acids and bases. No two acids go together and no two bases go together, okay? So I see an acid and a base on one side, and I see an acid and a base on the other side. So let's work with real substances, okay? When you're trying to identify the conjugate acid-base pairs, you want to look at the reactant side of the reaction arrow, and then you want to look at the product side of the reaction arrow, and you want to see like who kind of looks alike. So what I mean by that is, look at this. HClO2, ClO2 minus. Those guys look pretty similar, except this has a hydrogen in it and this guy doesn't. So what happened? This guy lost a hydrogen ion. It donated a hydrogen ion. Well, based on the Bronsted-Lowry definition, that makes this guy an acid. Things that give away their hydrogen ions are acids. How do we know that's an acid anyways? It has an H out front, right? That's how we used to identify them before. Okay, so who is its partner? Well, its partner is called its conjugate base. Acid-base pair. Okay, so either way, by default, if this is the acid over here, this has to be the base. So you go, oh, water's a base? That's weird. Yes, water can act both like an acid or a base, depending on what you need. And then again, how do I know it's a base? Well, if you look at water and what happened to it between here and here, it accepted a hydrogen ion. From who? From the HClO3, or HClO2, excuse me. So this guy lost its hydrogen and the water took it. They're like exchanging hydrogen ions. So this is a base, and this guy is called its conjugate, acid. So again, these are conjugate acid-base pairs. So we're going to do some more practice. I will do the first two with you, and then you can try the third one. So first thing I like to do, again, is try to like line up who looks similar to each other. So like, these guys look like HCl and Cl. And then like H2O and H3O, okay? So what happened to HCl? It lost a hydrogen ion. That makes it an acid, which by default makes its partner, right here, the Cl minus, a conjugate base. Okay, well that makes the water the base over here. How do I know? It accepted, it gained a hydrogen. It went from H2O to H3O. So that makes this guy its conjugate. I want to do that right. Acid. So these are the conjugate acid-base pairs. All right, let's try the next one. So I'm going to try to link up the things that look similar to each other. So HCl and Cl look alike, and NH3 and NH4 look alike. So what has happened to my HCl? It started off with an H, and now it lost an H. It donated an H, a hydrogen ion donor. So that makes it an acid. So its partner is its conjugate base. Now, that makes ammonia a base, which how do I know? Well, if you look from here to here, it accepted the hydrogen. So the HCl lost the hydrogen and the ammonia took in the hydrogen. So this is a base. Something that accepts a hydrogen ion is a base, and this makes it its conjugate acid. So I would like you to take a moment to try to identify the conjugate acid-base pairs in this last reaction. So is this what you guys got? This is the acid. It lost a hydrogen ion to make OH minus. If you have trouble seeing that, if you do find it helpful, rewrite water as HOH, because it's really H plus and OH minus that make water. 2 H's and an O. All right, any questions? Okay, this is going to be the last thing we do today. So amphoteric or amphiprotic is something that can act like an acid or a base depending on the reaction. So we're going to write out a reaction where we have this ion, HSO3 minus, and we're going to have water be our amphoteric species. So we're going to have it where, or no, I'm sorry, not water. We're going to have the ion be amphoteric with the addition of water. So what that means is I'm going to do two reactions, HSO3 minus plus water. And now these are equilibrium arrows, which you don't need to understand right now. Okay. Now, in this first one, I want the HSO3 ion to act as an acid. So we have to understand what acids do. Well, what do? They donate or give away their hydrogen ions. So I need to rip the hydrogen off of this ion if I want it to act like an acid. So what do I have when I rip the hydrogen ion off of it? I have SO3. Now it was already -1. So if you remove another +1 charge, the charge becomes -2. Okay? So look at my acid lost the hydrogen ion. Well, who took it? The water. So what does the water become? The water becomes H. It accepted the hydrogen, so now it has 3 hydrogens. And you have to be +1 because you added a +1 charge. Okay? All right. What about part B, where the ion acts like a base? Okay, well, what do bases do? So I need this guy to act like a base. So that means it's going to take in or accept a hydrogen ion. Well, from who? Well, from the water. So again, this guy is now going to have an extra hydrogen ion. So H2SO3. Now notice the charge goes away because hydrogen is +1 and the ion was -1, so they canceled out perfectly. Okay. All right, now what happens to the water? Well, this guy lost a hydrogen ion. So again, I'm going to rewrite water like this, HOH. So if I rip off the hydrogen ion, right, what do I end up? I end up with OH, and then again, it's -1 because you removed a positive charge from it. So again, this is called being amphoteric or amphiprotic, where the species can act as either an acid or a base depending on the reaction. You also notice that water acted as both an acid and a base in each reaction as well, because water can also be amphoteric.